Hello viewers, welcome to my channel. In this lecture video, I am going to tell you all the steps that are required for multiplying two numbers which are represented in IEEE 754 Floating Point Standard. Please stay till the end so that all the steps are clear to you. Please also like, share and subscribe my channel so that it motivates me to make more lecture videos for you. So let's dive in how to do floating point multiplication. So first of all, let's take a simple example where two binary numbers are getting multiplied. And this is called binary point. Digits before the binary point is the integer part and digits after the binary point is the fraction part. And you can notice that first number is called the multiplicand and the second number is called the multiplier. And you have done lots of multiplication in your schools where the numbers were in decimal numbers. Only thing different here is that it is binary and you already know the binary to decimal conversion. Here it is written this number here is equivalent to 3.5 in decimal and the second number is 3.25 in decimal. So if you have a calculator, you can quickly calculate it in your calculator and get the result. And you can later on verify whether the multiplication, where the numbers are in binary, is also giving you the same result. So you take this process of multiplying. This is the multiplicand, this is the multiplier. You start from the least significant bit, and if that bit is 1, you bring the multiplicand here. That means these are the partial products. We call them partial products, and you keep adding the multiplicand only when you are multiplying with a 1. If you are multiplying with a 0, that time you are not adding it. So and every time you are also shifting, you are shifting the partial product towards right, one bit at a time, and the product became this. And if you convert it from binary to decimal, it is 11.375, and if you have computed in decimal, you can verify it is exactly the same. Only here to notice the steps that are to be followed. So floating point numbers also, you will be doing the same thing, only the representation of the number is different here. So here you can see the steps again. In every step, partial product is shifted. Next bit of multiplier is examined. Also a shifting step, because you will be starting from LSB, you will move towards the MSB. And if the bit is 1, shifted multiplicand is added to the product. These are the process. And another thing to notice is that the product takes twice the number of bits as the multiplicand or multiplier. So you have to provide a big register which can hold this product. So the multiplication hardware is like this. You keep a multiplicand in a 32-bit register. In a computer, we are talking about computer. Our computers are either 32 bits or 64 bits. Here we are taking example of multiplicand, which is 32-bit. And we also have a 32-bit ALU, arithmetic logic unit. And here is the product register. So you can see ALU will take two numbers and add them. One is coming from the multiplicand and another is coming from the product. The partial product is coming from there, and those two numbers will be added. But as I told you, only if the multiplier bit is 1, that time it will be added. If it is 0, no addition, only the product will be shifted here. And you can see the product is 64 bits. Initially, in the right hand side, the multiplier is there and product is only in the leftmost 32 bits. And with every bit of multiplier getting multiplied, it is also shifting there. So the control unit is determining whether to shift or to shift and add both. So these steps are written here. 32-bit ALU and multiplicand is untouched. That means they are not changed or shifted. The sum keeps shifting right, and at every step, number of bits in product plus multiplier is 64. Hence, they have a single 64-bit register. And let's see the flowchart. It is the same which I have told you just now. Start and test the product 0. You test the 0th bit where the multiplier is there. If the product 0th bit is 0, then only shift the partial product to the right. And if the 0th bit of this product register is 1, then you first add the multiplicand with the partial product and then shift. And then you take, is the shift done? All 32 bits here, no? All 32 bits done. Then the multiplication is complete. If 32 bits are not done, the same thing will be repeated. So you can ask me that multiplier need not be 32 bits. So in that case, it will be stuffed with zeros in front of it. And then this process will continue. So now we have to see that the numbers need to be represented in IEEE 754 standard first, and then we have to do the multiplication. So these standards are either single precision, 32-bit, and double precision. And these standards were incorporated so that the programs written and executed by different computers, they all give the same result. For scientific calculation, the precision of the numbers is very important. Precision of the result is very important, and so a universal way of number representation was required, and that's why IEEE incorporated this standard in 1985. And the thing is that in this floating point standard representation of number, the dynamic range of number that can be represented is much more increased than the fixed point number representation. So that's why this floating point standard is taken by the computer's hardware. So this is the IEEE 754 number representation format, in which there are three parts. First one bit, most significant one bit, is for the sign bit, and then next 8 bits for the exponent part. And this exponent is biased. For single precision, it is plus 127, and this 23 bits is fraction. So the actual number that is there in this representation is x equal to minus 1 to the power sign bit into 1 plus fraction. This 1 is not given there, it is hidden, into 2 to the power exponent minus bias. Now the significant is the 1 plus fraction that can be represented will range from 1 to 2. Suppose the fractions are all 0, because there is a hidden 1, so it will be 1. And if the fractions are all 1, then it will be 1.1111. So it is very close to 2, but not exactly 2, because it will need other more bits to make it exact 2. So this is the representation, and you must take a notice that the single precision bias is 127 and double precision bias is 1023. If it is double precision, the whole thing is 64 bits, and here it is 1 bit, 11 bits, and 52 bits. So this is a number representation in floating point standard first. Before we do the multiplication, we represent the number in floating point. So if we have to represent a decimal number minus 5.25, then it will come out to be 101.01 in binary representation. And in scientific representation, it is minus 1 to the power 1 times 1.0101 into 2 square. And for floating point representation, we have to add 127 with 2, so it will become 129. 129 is equivalent to this binary, and the fraction part we will be keeping 0 1 0 0 1 0 1, and all other bits are 0. And for double precision, this is 11 bits, bias is 1023, and the fraction is like this. Let's see the multiplication steps when the numbers are given in scientific notation. First example which we saw in the beginning, it was just a simple binary number. It was not in any scientific notation. So scientific notation has exponent part. So we must see that first. So these are the two decimal numbers given in scientific notation, and they are 4-digit number. So the first number is 1.110 into 10 to the power 10, and the second number is 9.2 into 10 to the power minus 5. So when we multiply, we add the exponent. You must have known it already, because you have done this kind of multiplication in school. And then we multiply the significand, and later on we attach the exponent part. So right now this number, the result is not normalized or scientific notation, because before decimal point there are 2 digits. So there should be 1. So we are shifting the decimal point and adjusting the exponent. And because the result will also should have 4 digit, we need a rounding. So we are dropping the fifth bit here. And the result given in scientific notation is this. For floating point number multiplication also, we are going to follow the exact same steps, only there the floating point numbers are of fixed, some width is given 32 bits or 64 bits, and there are 3 parts are given, no, where to keep the sign bit, how long is the exponent, that means how big the number can be or how small the number can be, all are specified there. But the procedure will be the same. First is add the exponent, second is multiply significand, third is normalize the result and check for over and underflow, whether the result can be kept in the specified number of digits or not, and then round and re-normalize if necessary, and then determine the sign of the result from sign of the individual number. If both are positive, then the result is positive. If one of them is negative, then the result is negative. So we all know this, but just to recapitulate. Now we see the same example, multiplication example, but here the numbers are binary and given in scientific notation. So these two are binary numbers. So here also you are adding the exponent, then you are multiplying the significand, then normalize the result and check for over and underflow, then round and then determine the sign. So after all the background, how to multiply, how to represent number as a floating point, we are going to see how to multiply the floating point numbers. Now suppose we will be multiplying two numbers, minus 0.3 times 248.5. This is in decimal, so you can use a calculator and find the answer already, and then later on you can verify it. So there are several steps in representing the number in floating point. So this is the number 1. It has a mantissa into 2 to the power exponent. So this mantissa is actually 1 plus fraction 1, 2 to the power exponent. So 0.3, it has a repeating pattern. 0.01, after that 0011, 0011, and it keeps on going, it never ends. So that's why, because we have to represent the fraction, no, first of all this is the translation of 0.3 to binary, and it was not normalized. No, in case of normalization you have to have a 1 in front of the binary point. So when you normalize the number, you also get the exponent, which is 2 to the power minus 2. And as I said, you only have 23 bits in the fraction part, so you have to round now. You take the 24th and then you add it with 1. It is called rounding up. There are many rounding techniques are also there. So in this case, we are rounding up. So it will become 0 and this 22nd bit will be 1. So this is the translation or conversion of the decimal point 3 to binary in scientific notation. So this is the fraction part. Exponent is -2 and you add the bias, it becomes 125. So this is the exponent. So the whole number is written here. First the sign bit 1, then the exponent, and then the fraction. Similarly for this number 248.5, this is the conversion from decimal to binary, and now after normalizing you are getting 1.1111, this number. So from there you are taking the fraction and you are noticing the exponent 7, and biased exponent will be 7 plus 127 is 134, and in IEEE 754 format it will be 0 because it was a positive number, then the exponent, and then the fraction part. Now we are going to do the multiplication. Here the multiplication is shown exactly the same way. And remember previously also when we were multiplying the numbers, we just ignored the ignored the binary point, and later on in the product we placed the binary point. In the first example also we have done that. Done that. So here this is the first number. Here I have written the hidden one and the fraction. All together it is written. And here also for the second number also hidden one and the fraction. Those will be multiplied. Okay. So if you do the multiplication, I have done the multiplication. These red color ones are all the carries that were produced here. So we have only first you multiply by 1, you keep the multiplicand here, and then you have to shift, no, that is even here with a cross, and then you see that there are 3 zeros are there. So for that you do not add the multiplicand, so they are also given with a cross mark here. So then when you multiply with this one, then it comes here, then you again shift. Okay, so basically you are adding 6 rows of 6 partial products you are adding, and you are getting this number. So where to put the binary point now? This one has um, it should be 23 bits, right? 23 bits, but there was a 0 here, the LSB, that I have ignored here. So here it is taking the hidden one. There are total 23 bits, and here it is 1 2 3 4 5 6 7 8 9. So 22 plus 8, 30 bits. So from the right hand side, uh, it will have 32 bits, and then you will be putting the binary point here in the product. Okay, so it came out to be this big number. You can see it has many more bits than floating point can represent, so we also have to do some rounding. But first of all, when you put the binary point before 30 bits, you also have 2 other bits in front of it, so it is not normalized representation. So you have to shift the binary point and it will become 2 to the power 1. So this is a scientific notation, but you also have to do rounding because you only can keep 23 bits in the fraction part. So if you round, you add this one with this. We are always rounding up. You can just ignore also, and there are many other ways of rounding that is also provided by IEEE standard. In some other video I will go through all the rounding technique, but here you note that we are always rounding up. The first number 0.3 also we rounded up, and here this product I am also rounding up. So this one became 0 and this one became 1, and here it became 2 to the power 1 because you had to re-normalize the number, and that will be added with the, when you add the two exponent, it will be added. So let's see. So n was this. So you first of all you have to do what will be the sign of the two numbers. It will be first number sign XOR second number sign, and then M1 into M2 mantissa into mantissa, which is the 1.00, everything together, and then 2 to the power E1 plus E2. In IEEE 754 format, because this exponent already has 127 added, 127 is added, so you will minus 127. So it will be minus 2 plus 7 plus 127. I didn't add this 127, 127 and minusing. Basically, there is only 127, which is 132, and it is given here. And M1 into M2 was given here, this one. So now your new exponent will be 132 plus 1, because here is 1, you got a extra 1 as exponent when you normalize the number. So new exponent is 133, and this is this. So the answer of the multiplication in IEEE 754 is this. So if you convert this number in decimal, then you are getting this 74.55, where if you do the decimal multiplication, it is coming out to be 74.55 only. But here you can see, here you have a 3 also, and I didn't compute much more. So this floating point arithmetic, this multiplication is approximate, and it is giving a little bit higher result, because remember, you round it up twice, once when you are representing 0.3, and also in the final product, you round it up in the 23rd bit position. That's why you got a value that is little bit more. So if you use a double precision standard, your result will be much more precise. It will be less than this 3 will not be there, maybe it will be much less. So basically what you have done for multiplication, you are doing XORing the sign of A and sign of B, two numbers A and B, and you are adding A's exponent, number one's exponent, number two's exponent, and you are minusing the bias ones, and then you need a normalizer, and you are multiplying number A mantissa and number B mantissa, and you have to use a normalization again, and this one is giving you the result. So the procedure for multiplication is add the exponent and subtract the bias, and XOR the sign bits and multiply the mantissa. So let's see the hardware for it. This is the two IEEE 754 floating point numbers, sine, exponent, fraction, sine, exponent, fraction. So you are taking the exponent and exponent, you are adding them. In the multiplication, you add the exponents, and then you are subtracting 127, because two numbers have two bias added, so you are subtracting one of them, and then you are multiplying 24 by 24. It is 23 bits in the fraction part, but now this time you have considering the hidden one also, so it became 23 plus 1, 24 bit for both the numbers, and you are creating the product, but you have to round, right, and you have to renormalize also. So ultimately you will represent as 23 bits, so rounding is needed, and a renormalization is needed. Whenever you have to renormalize, you are adding 1 with this exponent that you have already computed, and this is the hardware for floating point multiplier. And the flowchart or the algorithm is also the same. Start at the biased exponent of the two numbers, subtract the bias from the sum, and to get the new biased exponent. Then multiply the significance or mantissa, normalize the product if necessary, shifting to right and incrementing the exponent by 1. And now here another thing you are checking is overflow or underflow. Overflow and underflow occurs only when you are adding two exponents, right? You have only 8 bits to represent your exponent. And when I have gone through the foundation of floating point number representation, I have told you, no, in 8 bits of exponent, you can represent the number ranging from minus 126 to plus 127. If the addition of two exponent is more outside that range or too less, then it is called overflow or underflow, and you are checking it here instead of checking when you added the exponent, because when you are normalizing the number, you are adding 1 with the exponent, no, that time also it may overflow or underflow may happen. That's why this check is given here. And if yes, then it is an exception, the number you are calculating is not right. And if there is no overflow underflow, then you are rounding again, which the round procedure I have already shown you. And then it is saying, is it normalized? After rounding also it may be not normalized, then you are taking it back here again to normalize. And if it is normalized, then set the sign of the product to positive if the signs of the original numbers are positive, otherwise it is minus. Okay, so this is the flowchart. So here again I am talking about this exception. What is that exception? As I told you, this exception may happen when there is overflow or underflow in adding the exponent. It is just like any other integer overflow or underflow. So overflow means result is too big to represent in those number of bits, and underflow means result is too small to represent. Both can raise an exception under IEEE 754. For an unsigned number, overflow happens when the last carry cannot be accommodated. And for a signed number, overflow happens when the most significant bit is not the same as every bit to the left. When the sum of the two positive numbers is a negative result, that is not possible, right? So it is a overflow. And when the sum of the two negative numbers is a positive result, and that is also not possible. The sum of positive and negative number will never overflow. So you learned a lot of things. There are a lot of steps there which are needed for multiplying two floating point numbers. Hope everything is clear, and I will come up with another video where the rounding and overflow and underflow is covered in more detail. Hope you like this. If you liked it, please like, share, and subscribe. And thank you for watching my video.